All right, so guys, today section 9.7 probability. Uh, you know, may as well just be consistent. I think we've said it every section in chapter 9 so far, but the reason for the reason for chapter 9 is it's twofold. It's absolutely part of what we're trying to do and accomplish here in pre-calculus, but again, we're really keeping an eye on that ACT as well. The ACT exam, according to ACT. And again, we're going to touch on ACT. We're not going to touch on it. We're going to do a deep dive second semester as we get a little bit closer to our state testing day, things like that. But they, meaning the ACT Corporation, they claim 5 to 7 of the 60 math questions are probability-based, probability-related. So again, a lot of the types of questions that you have seen or will see on the ACT are literally being pulled out of the section that we're talking about today. So the very good news is that probability is not new. You started probability things. Again, it's very, very simple probability in elementary school, and it's grown with you as you progress. But this is something that is hit relatively hard in Algebra 1. Not a lot in geometry, to be perfectly honest. There are some geometric probabilities that were found. But then it's a bigger deal in Algebra 2. Now it's a bigger deal here in pre-calculus as well. So if you find yourself going into AP Statistics next year, you better believe you're going to be doing a lot of the probability stuff. AP Calculus significantly less. But again, this is kind of one of the pillars of what we're talking about in high school mathematics. Good news is, once we understand the terminology and a couple of the the ways of setting things up, I would be surprised if people are nervous about probability. It's I would say that there's probably only like a 26% chance or something like that. No, too soon for jokes. All right, gotcha. All right. Put a red line through the probability joke. Okay. All right. So the goals that we have in mind here is that students be able to find the probabilities of events and their complements. Number 2, students to be able to find the probabilities of mutually exclusive events. Number 3, students to be able to find the probabilities of independent events. So one of my main focuses here today is we've got to walk out of here knowing the difference. We've got to understand what mutually exclusive is all about. And then also we have to be able to tell the difference between this is mutually exclusive as compared to that is independent. And again, the main reason why we care so much is that, for lack of a better term, the formula for mutually exclusive is going to be significantly different than independent. Again, simply put, we're going to be adding one, we're going to be multiplying the other. So again, we have to know what we're looking at as we dive into that. All right, so guys, we're going to be focusing, excuse me, here today. We're going to talk about probability in terms of we're going to hit the basics, we're going to hit the terminology, we're going to hit the notation, we're going to hit the rules. Then we've got some examples as well. But again, we're going to try to break it down into those little categories. So the basics of probability, which honestly I'm very tempted to just gloss right over this, not even mention it. But again, there is a chance that somebody out there is feeling less comfortable with probability. But again, when we talk about probability, again, we're going to generally use this capital P for probability, right? So the probability of an event, whatever the event is, could be, like I said, flipping a coin, drawing a card out of a deck, or whatever the probability is. The probability of the event, we're going to look at it. I always like to think of it as target divided by total. Our textbook writes it up as number of successes divided by total number of outcomes. I think it's just simpler, target divided by total. Okay. If I were to flip a coin and I want it to land on heads, what are you going to tell me that probability is? 50%. Okay, that's what I heard loudest. Did anybody say anything else? Anybody have another way of saying that? 0.5. 1/2. Okay. Now, those are the 3 ways that we're going to be presenting. So we'll come back to that here in a little bit. But if we're flipping a coin, we know that there's 2 outcomes. It's going to land on heads or it's going to land on tails, right? So there's a total of 2. The target was landing on heads. If I'm looking at the coin, only one of the outcomes is quote-unquote heads, right? So that's why we would say target divided by total, 1 divided by 2 is how we would get there. Now, we could, one of the, I don't know if this is a good thing or a bad thing, frankly, about probabilities, but you can find a probability on pretty much anything, right? Again, if you can associate numbers to something, you could divide those numbers and essentially calculate a probability. So, again, we could have everybody put your name into a hat, and then we could figure out what's the probability that I randomly draw the name of someone who's left-handed, for instance. How many people are left-handed in here? 4? Okay. So 4 out of 26, I think, is what we've got in here. So 4 out of 26. So we'd have a 4 in 26 chance of pulling that off, right? Okay. So again, it's all about the target divided by the total. What if we change the target? What if we said, no, okay, I misspoke, sorry. We want to pull somebody's name that is not left-handed. How about that? Now, would we have to recount? Should I have everybody raise their hand if you're not left-handed? No, we could use the complements, and we could just say, all right, well, if there's 26 total, and we know that 4 are left-handed, 26 minus 4, 22 are not left-handed. Now, are you noticing the terminology that I'm using? Because with probability, things can be a little specific. You'll notice that I'm not saying that, okay, well, left-handed, immediately I'm not jumping over to saying who's right-handed. Okay? I'm saying it as who's not left-handed. Does that make sense? Okay, we have to look at it that way in terms of probability, because there's always those special cases out there. What about that person that's ambidextrous? What about that person that doesn't have arms? I don't know. I mean, but there's all sorts of... I'm serious. Yeah, you got to say that person's not left-handed, right? That is kind of funny to think about. Yeah, but you get where I'm coming from, hopefully. All right, but I've never thought about that. Like, in all seriousness, what if somebody was born without arms? And they have to answer that question. Are you left-handed or right? That's what I'm saying. Is,
You can't click on the button, so you can't answer.
yeah, I don't know. Anyway, my mind is going in a different direction here. Okay, so like you were telling me when I was asking you about the whole flipping of the coin thing. Again, the probability that lands on heads, you told me, I heard 50% loudest. Again, that I think that most of us associate probability with percentages, usually. But we also talked about fractions, we talked about decimals, and those are actually the 3 ways that we're going to be presenting the answer. I would say, again, in our class, fractions and percentages are going to be the 2 most common. Okay, oftentimes the directions will ask as kind of a cover your backside thing. If the directions do not ask, I would do both reduced fractions and decimals. Or, excuse me, reduced fractions and percentages. If the percentage has a decimal, I would, again, assume that we're going to round to the nearest 10. Okay? All right, next up is sample space. Sample space, by definition, we say that it's going to be the set of all possible outcomes of the experiment. Sample space is easy, but it's tedious. Basically, all that you're doing is you're going to list out all of the different ways that you could do something. What are all the possible ways that we could flip a coin? Well, if you're talking about just flipping a coin, just tossing a coin, the sample space is really simple. What could it land on? Heads. Land on tails. There's our sample space. The only thing that we have to watch out for is that weird kind of brackets that we have around. Ethan, what was that? I always have somebody who asks that. What if it lands on the side? No, you don't. You don't have to say it. You don't. All right, yeah. We're going to assume that we live in a world to where the coin does not land on its side. I've been around for a long time, and I've never seen a coin get flipped and have it actually land on its side. But every year somebody says, well, what if? I'm sure that could happen. Probably. But until I see it happen, yeah. All right, what about the sample space of tossing 3 coins? Okay, like literally, like I have 3 coins in my pocket, and I pull my hand out of the pocket, I drop 3 coins on the ground. What are all the ways that they could go? Head, head, head.
Heads, tails.
Head, tails.
Tails.
Now you're just saying letters. Okay. Heads, like that. Now, are there any other ways that, again, looking at the way that I just wrote this up, the second, third, and fourth entries that I just wrote, would you agree that all 3 of those had 2 heads, 1 tail? Are there any other ways that I could write this up where we have 2 heads and 1 tail? Nope. Okay. So next up, what about 2 tails, 1 head? Like tail, head, or tail, head, tail, or head, tail, running out of space. Okay? Any other ways that I could write 2 tails, 1 head? All right, so that leaves us with one more option. What is that? Tail. again, hopefully you agree with me when I say that it's not hard. It's just kind of tedious. It's just a hassle to write everything out. The bigger the sample space, the more writing you have to do, right? What about here in number 3? You flip a coin once, and a 6-sided die is rolled once. And we've got 2 separate things that are happening. So if I flip the coin, what could it land on? Land on heads, or it could land on tails. All right. So if it lands on heads, could I have it land on heads and roll a 1? Heads and a 2. Heads 3. Heads 4. Heads 5 and heads 6. If I flip the coin, have it land on heads, are there any other options? No. We also have that possibility of flip the coin, having it land on tails. It could be tails with 1, tails 2, tails 3, tails 4, tails 5, tails 6. But that would be my sample space. Ben, I see a slight smirk here.
What if the die lands on his corner?
Oh, I knew that somebody was going to go that direction. Yeah, I've never seen it happen, so I'm not too worried about it. Living in the land of what ifs. All right, so guys, next up, we've got some terminology. Here. First up is this concept, this notion of being mutually exclusive. Can I get like a quick thumbs up, thumbs down? How many of us, forget about meaning, how many of us feel like, yeah, I've heard that phrase before? Okay, good. How many people feel like, and I think I know what it means? We had some thumbs go down. Okay, all right, so here's the deal. By definition, and I don't know how helpful this first part of the definition, we say mutually exclusive, the events are disjoint. Okay, now what does that mean? That's like using a weird word within the definition. Again, we have definitions for clarity, and then you throw a weird word in there, didn't make it much clearer. Okay, but basically, again, this second bullet point I'm trying to highlight here: the events do not share possible outcomes. That I think that's a little bit more clear as far as what we're talking about. Okay, it literally comes down to these 2 things cannot happen at the same time. It would be impossible to have these things happen at the same time. So through that, I came up with this sweet drawing here. It's pretty clever. I'll send it out to you guys if you want. But again, these are all the possibilities of event A happening. These are all the possibilities of event B. And you can clearly see there's no overlap. Okay? So what I think might be the easiest demonstration would be deck of cards. Okay? Could I shuffle these up? And I'm gonna draw out some cards here. I shuffle them up. Could I pull out a card that is both a club and a diamond? Could I pull out one single card that is both? Oh, that's both a club and a no. Those are mutually exclusive, right? The club of diamonds. Yeah. Could I pull out one card that is both a 5 and a king? No, these are mutually exclusive. Now, could I pull out a card that is a 5 and a club? That could happen. Those are not mutually exclusive. Are we starting to see the difference here a little bit? Now, the difference in where we're going here next with independent events. Independent events, by the way, we define as, we say that the occurrence of one has no effect on the occurrence of the other. But I want to focus on this piece here. Focus one and another. The difference between mutually exclusive and independent is mutually exclusive. We have one thing happening. You're drawing one card out of the deck. Okay? We said that, okay, can't be a, what did I say? Can't be a 5 and it can't be a king. Those are mutually exclusive. Or it can't be a club and it can't be a diamond or whatever it is we said previously. Those are mutually exclusive. But at the end of the day, you were drawing out one card. Down here with independent events, that would be like, what's the probability of drawing the 10 of diamonds and flipping the coin and having it land on heads? Now, do you see how we have 2 different events that are taking place? Okay, now the big difference here is that when you're talking mutually exclusive, the way that we mathematically calculate that is going to be very different than how we're going to mathematically calculate down here, okay, with independent events. All right, so again, a little bit more on that as we go here for sure. Again, when we're talking about probability, we've already hit on the fact that we're talking about percentages. Probabilities have to be between 0 and 1. You could have a 0% chance of something happening. It'd be like if we had you all put your names in a hat and say, okay, what's the probability that I draw a freshman's name? 0%. None of you guys are freshmen. Okay. We could have a certain